Okay, so I will sketch the proof of the denseness result for a minimal surface, and also then sketch the proof of the equidistribution theorem. So I'll state the theorems. So let's call this theorem A. This is joint with Kairi, Fernando Marquez, and myself. This was in 17. And the theorem is that let's assume that the ambient dimension is between 7 and 3. Then the theorem is that for a C infinity generic set of metrics, on a closed manifold of dimension n plus 1g, then the set of all closed minimal hypersurface. And when I say minimal, I always mean smooth and embedded. Minimal hypersurface is dense. Okay. And theorem B is joint with Fernando, myself, and Antoine Song, and again from 17, and is under the same conditions, under same hypothesis. We can find a sequence of minimal hypersurface, sequence of closed minimal hypersurface, closed minimal hypersurface, such that for every ambient function, such that this sequence equidistributes in the following sense. If we take some ambient function, and then if we sum the average of the function on the first Q minimal surface, and if we divide by the sum of the areas of this minimal surface, and we make Q go to infinity, we recover the average of the function on the whole manifold. So this is the same thing as 1 over the volume of M, the integral of M of F dV. Okay? So I want to explain how to do these two theorems, but the thing I really want to make sure it comes across is that there are essentially two ingredients, and from these two ingredients, we will deduce these two theorems. And the interesting thing, from my point of view, is that these two ingredients you can find in slightly different scenarios. And in that case, you also have denseness and equidistribution. For instance, in yesterday's talk, I mentioned this result of Kairi that uses embedded contact homology and Seiberg-Witten-Floer homology, which are things that I surely do not understand. But the thing that proof has in common is that there's also a Vi law, and there's a spectrum, and there's like a Minimax theorem, and using these things, it deduce the denseness of the geodesics. Okay.
Denseness in the space of hypersurface?
No, in the manifold. So it means the following, that if U is open set contained on M, there will be a closed minimal hypersurface that passes through U. Then there exists sigma closed minimal hypersurface, let me just call it surface, such that sigma intersect with U is non-empty. So we have an ambient manifold, could have topology, right? Something like this. We pick any set U there, And for sure, there's going to be in this case, there'll be a geodesic which will pass, it's closed and passes through that set U. Yeah.
What happens for large n? This theorem is still true?
For large n, as in the ambient dimension. So I would expect the theorem to be true. What happens is when n is large, then this minimal hypersurface start having a singular set, and then you have to, you'll see in the proof, eventually we use implicit function theorems and we use tools that require one or two derivatives. And as soon as you use that, then the existence of a singular set, you have to worry what to do that, and we didn't want to consider that. Yeah.
Is there some problem that goes wrong with the Sobolev inequalities in higher dimensions?
In what sense?
That you don't, if you have two derivatives, you don't get as much out of it as you do in lower dimensions.
Yeah, I don't know. It could be, but I don't think so. It's just this. I would expect the theorem to be true in any dimension. Okay, I would expect the theorem to be true in any dimension, and the proof doesn't exactly apply straightforwardly because the hypersurface will have a singular set, and so you have to worry when you use implicit function theorems, then that becomes an issue. But I would expect the theorem to be true in any codimension, in any dimension. Okay. Any other question? Okay. So let me tell you the two ingredients. So the first one is this notion of volume spectrum and Weyl law. Weyl law. So the setting is the following. So I'm going to consider the space. This is the space of all hypersurface which bound the region. So this is the space of all boundaries where omega is a region. Okay. So the guiding result here is Almgren, which show that this space is weakly homotopic to RP infinity. And so they must have the same cohomology. And thus, the cohomology ring of this space, if we do coefficients in Z2, is just Z2 with one generator. So there's just one generator, and the cup powers of this generator generate everything. Okay? And we use this now to define the volume spectrum. So now we have, and so out of this, we say that given X, a finite dimensional complex, for instance, you can imagine that X is just some p-projective space. For instance, X is just some p-projective space. We say that a continuous map from X into the space of hypersurface, continuous, is a p sweep out if when I pull back the generator and I do its cup power with itself p times, I get something non-zero in p cohomology of X Z2. So this is an algebraic condition, but it has a very geometric interpretation that essentially is the reason why we call it a p sweep out. The geometric interpretation is that, so this is a map from a space, say with p parameters, into a space of hypersurface. So every point we map to a hypersurface. Then we call it p sweep out because this map has the following property. If I take p points on the manifold, there's one element there whose correspondent hypersurface will pass through these p points. So if it's a one sweep out, it means that if you pick any point on the manifold, then there's one hypersurface in this family that passes through that point. A 2 sweep out, it means that there exists one element which is hypersurface that passes through these 2 points, so on. So that's the notion of a P sweep out. And one can construct these things, okay? But now the important thing is, as soon as I have them, I make like this nonlinear spectrum. Omega p, they depend on the metric, and this is the following. I look at all P sweep outs. And for each P sweep out, I maximize, or I take the soup, I maximize the area. So let's just, of X, of the area of this P sweep out, okay? We've seen a similar formula like that when we were defining the Pth eigenvalue. So it's formally is the same.
Is it possible to give any intuition for why this sweep function equal
Okay, so so the way we do this is we show that the first fundamental group is Z2, and then we show that any other homotopy group vanishes. And so it's a space which has the exact same homotopy groups as Rp infinity, so it's weakly homotopic to Rp infinity. Now, let's show that pi1 is non-zero, right, of this space. Oh, sorry. Okay. So intuition. So let's show that this one is Z2, right? So I need to find the element, right? So there's the manifold, and just take some Morse function itself, right? F, and we can make the Morse function with values between 0 and 1. And now I'm going to take the following map, phi, which goes from 0 to 1 into this space. And what the map does is phi of t is the boundary of the set of points where f is less than t. So phi of 0 is just the 0 set. You know, phi of t is essentially just the level surface, right? And phi of 1 is the boundary of everything, which is 0. Now the remark is that phi of 0 equals phi of 1, which is the same point, is 0, because it's the boundary of the empty set and the boundary of everything, and there is no boundary. And so this is not a map from an interval into there. This is a map literally. Here I identify 0 with 1, and so this is a map from S1 into there, and this map is homotopically non-trivial. Okay? One way of seeing that is that if you deform this map in any continuous way, there has to be a slice which cuts the volume in half, and that slice, the area will always be big. Okay, so this takes care of that. Now, how do I know that the other homotopy groups will be 0? And so the remark is that there is a 2 cover of this space, which is contractible, and that's enough. So let's just do this one. You know, where k greater or equal than 2. So let's recall. So the space is a space of boundaries. So the obvious to cover is just the regions. So let's consider this, right? Here I have the space of boundaries. And there's a 2-to-1 map, which is the space of regions. And the map is just the boundary, right? It's just omega is mapped to the boundary of omega, and it's 2-to-1 because if you take any region, then it's the boundary of exactly 2 guys, the bottom part and the top part, right? So this is a 2-to-1 map. And you can see that this is contractible because if you have any region, you can just so, you can, so if you have any region, I can just use this Morse function to homotope this to 0. It's not hard to see that any region is contractible. You can just, so if you have this region, you can just surely decrease it to a point, right? There's no thing. And so this space is contractible. And so now if you have a map from a K-sphere into there, because K is bigger than 1, it meets a lift, this space is contractible, so the fundamental group there is 0. I don't know. Was this okay here? Yeah, it's okay. 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 So now let's, so now there's an important result here, and this is due to Fernando, myself, and sorry, let's put Yevgeny first. Yevgeny, Marcus, and myself. And the result is that individually, each number depends on the geometry, but asymptotically, they will not. So the result is that there exists some universal constant, alpha n, just depending on the dimension, so that the limit, when k goes to infinity, or p, let's call it p, if I do the p width, if I divide by the growth power, I'm going to get this universal constant. But of course, this depends on the volume. And then you put just volume up to the appropriate power to make it scale the same way. Okay? We call this the Vi law. Okay? So it says that asymptotically, these numbers, they only see the volume and nothing else, regardless what the ambient manifold is. Okay? So this is the first ingredient. And the second ingredient is the Minimax theorem. So let me just state this. So the second ingredient is the Minimax theorem, which makes the connection between these numbers and the theory of minimal surface. So this was done by Pitts, Shane Simon, and Fernando and myself. Okay. So the theorem is that for every integer p, there exists sigma p, a minimal surface, a minimal, a closed minimal, a closed embedded minimal surface, right? But let's just write closed minimal surface, meaning hypersurface, so that the area of sigma p is exactly this number, and its Morse index as a critical point is less or equal than p, okay? So the two ingredients will be the existence of the spectrum, which has a universal law, and the existence of a theorem connecting the spectrum with some special type of critical points, which in this case is minimal surface, okay? So let me do an analogy with the eigenvalues, because a lot of the intuition we came up on while we're thinking on this problem came always from looking at what was going on in spectral geometry. Okay, so let's just do the following comparison. So compare. Okay, so this is the example where we know existence of a spectrum is for the Laplacian. So we have this sequence of numbers. This is the Laplacian, the spectrum of Laplacian. And there, there is also a Y law. Now, I don't know the powers by heart, so I have to look at my notes. So for the spectrum of the standard Laplacian, there's the Y law, which says that there exists some universal constant, which we know what it is, such that if I do the limit when p goes to infinity, if we take at the pth eigenvalue, divide by its growth rate, then we get a universal number, a of n, times the volume of m to the power of 2 over n plus 1. Okay? The difference between this Y law and that Y law is that in this case, this number is unknown. So this is actually alpha n is unknown. What the number is unknown. In this case, a of n is known because there are many examples in which you can compute the full spectrum, and as soon as you can compute this in an example, you can take the limit and you can just see what the number is, right? You can do it on a disk. So this case, the number is known. I mean, it's not this number is known. A of n is known. The reason is that this is like a linear spectrum, and this is what Gromov calls it, a nonlinear spectrum. So there's no example for which one can compute all these numbers except S1, because it's just points. That one is easy. So
What is it? It is known. What is it?
okay. So I mentioned two things. One thing is that this nonlinear spectrum, we can't compute it on any example. So if you take a two-sphere, we don't know what the values are. The only example where you can compute it is for S1. Because on S1, the hypersurface, they are points, and so that is very easy. But in any other case, it's not known. For the Laplacian spectrum, people know how to compute on tori, on spheres, and on disks. And there are other examples. So because we know the critical points are eigenfunctions, and we can say what they are. Okay. Here, there's also, so there's a spectrum, there's the Y law, just like in that case, and there's also a min-max theorem, right? The min-max theorem there is that for every integer p, there exists, let me call it phi of p of smooth function, so that it's an eigenfunction, so that the two things going to happen. The integral of the energy divided by the L2 norm, this is equal to the pth eigenvalue. And the second thing is that, of course, it's an eigenfunction. Okay? And so let's keep with this analogy. And in this case, there's also what's known as the local Y law, which in some sense makes our equidistribution theorem more natural. So let me write it. Let me write. So there's a local Y law which says the following, that for every continuous function on M, then if we integrate the function against the ith eigenfunction square on M, and if we sum over the first q terms, and if we divide by the sum of the first q terms of the integral of the L2 norm of the eigenfunction, then as q goes to infinity, this just converges to the average of the function on the whole manifold. Okay? So at the formal level, this resembles our equidistribution result. I divide the integral of the function over the first q elements over the total area. Okay, exactly just what I did. So what we are our equidistribution result is like the local Y law for minimal surface. And now, keeping with this analogy, there's a beautiful conjecture. It's called due to Sarnak. It's called Quanta unique ergodicity. So let me just say this. Because then this conjecture motivates conjectures on minimal surface. So that's why I'm bothering telling you about this. This is called Sarnak. This is due to Sarnak, and it's called Quanta unique ergodicity. And the conjecture is the following, is that if the geodesic flow is ergodic, then a strong equidistribution holds. Is ergodic, then the stronger form of equidistribution holds, which is just saying that if I integrate f against the I eigenfunction and I divide by the total L2 norm and I make I go to infinity, I converge to the integral of f dv. Okay? So the difference between this and that is saying that we don't need to take a sum. We just integrate a function against the ith eigenfunction, make I go to infinity, and we always converge to the volume. So this is stronger form. And so the expected results in our case, it would be that we conjecture that so because the local y law that has no conditions on the metric, meaning the local y law holds always. It doesn't need a genericity condition. We also suspect, so this is a conjecture between Fernando and myself, and the conjecture is that theorem B, which is the equidistribution for minimal surface, the way we stated, holds for every metric. For every metric in every dimension. Okay. Then the second conjecture, which would be our version of quantum unique ergodicity, it's I think we should all. I mean, we only conjecture for bumpy metrics. So let me say this: if M1 plus Z is bumpy metric, I will say what this is in words, and I'll write definition tomorrow. Bumpy metric, which is a generic condition. Then, if the P width equals the area of sigma P, where sigma P is closed, minimal hypersurface, closed minimal hypersurface, then in this case, for every continuous function, if I integrate the function on sigma P and I divide by the total area of sigma P and I make P go to infinity, I converge to the average of the function f. So bumpy metric, I'll just say it simply now. So whenever we are dealing with functions on manifolds, there is this standard notion of requiring a function to be Morse. It means that the critical points should be non-degenerate. So being bumpy is requiring that the area functional on the space of all hypersurface is Morse. And this is a generic condition. So if you take a function, if it's not Morse, you wiggle a bit and that becomes Morse. Okay. So now okay, so what I'm going to do now is I will prove theorem A and theorem B, and I mean I will just say what the main idea is. So this proof. So I should make a disclaimer, of course. I find the subject of minimal hypersurface and minimal surface beautiful. I find geometric measure theory a beautiful subject. A little downside to it is that it's super technical. And so because it's heavily technical, it's hard sometimes to, if you're just learning, it's always a bit painful to read the papers because it's not easy reading. So what I'm going to do is, of course, I will disregard every possible technical detail and just explain the key idea. And then if you're interested, you can start digging in the papers and start reading the reference and eventually get something out of it. But I do have the the impression that these basic ideas I'll tell you, they could be used in other contexts because they are not sophisticated at all. So they are elementary in some sense. Okay. So let's prove the first theorem. Okay. Is this okay here? Okay. So let's prove the theorem A. Okay. So what I want to see, I want to, okay, so let's start with the definition. So let's call S of G. This is the set of all, this is a set of closed, minimal, embedded hypersurface, closed minimal hypersurface of M with respect to the metric G, okay? So as far as we know the set is non-empty. That was the theorem I presented last time, and we actually know it has always n plus 1 elements, but that's it. I mean, so this is what one knows. And what we would like to see, we want to show the following. So what is the goal? The goal is to, let's fix U contain on M an open set. So I want to find some sigma in this element such that sigma intersects U. Okay. So there's my manifold. I pick some open set U. I want to make sure there's a minimal surface that passes through that set. Okay. So this is the goal. And if I can do this for every open set, then I know I have denseness. Okay. So let's okay. So to do that, let's look at all metrics for which that property is true. So let's define M of U. This is the set of all metrics G such that there exists a minimal surface with respect to that metric such that sigma intersect with U is non-empty. And one more condition, and a non-degenerate condition, which we're going to ignore because it's not crucial, and a non-degenerate condition. Okay. So the important part is I fix U, I look at all metrics which have the following property. With respect to that metric, I can find a minimal surface that passes through U. Okay? So I want to say that this set is open. And the reason why the set is open is because I have this non-degenerate condition. The set is open. Yes, because of non-degenerate condition, which I didn't say what it is, but because of the extra condition. So let's just ignore it.
Is the condition on sigma or the metric?
It's a condition on the metric. No, on sigma, sorry. It's a condition on sigma. It's saying, so I might as well say, it's saying that the critical point is non-degenerate. And the reason why I require that is because to know that it's open, suppose I have an open set U, I have a minimal surface that passes through there. If I wiggle the metric, I want to wiggle the surface. So I want to use the implicit function theorem, so I need some operator to have no kernel, and this is what this condition is requiring. Okay. So, but that's the purpose. But the condition is not essential. So if I show that this set is dense, then I'm done, right? If this set is dense in the space of metrics, then I'm done, because then I can just take a countable basis of open sets. I intersect this set for each element in the countable basis. I get a countable intersection of open and dense sets, and that is generic in the bare category sense. So let me just write that down. If MU is dense, we are done. We are done because if I take, say, a countable basis, then M, which is the intersection of all these open and dense sets, is generic. Okay, and is generic in bare category sense. Is generic, and we are done. In bare category sense, it's called a residual set. In bare category sense. So the thing I want to be able to prove is that this set is dense. And one thing we do in the paper is to show that this set is dense if the same set without this condition is dense, so you might as well ignore the condition. So that's the first step we do. So let's just doing that, which is let's remove that condition and show that this slightly large, and we show that the slightly larger set is dense, and we prove in the paper that if the slightly larger set is dense, the smaller one is also dense. So let's just ignore this condition now. And let's just show that this set is dense. Okay? So let's do that. So choose symmetric G0. I want to make sure that I can find a tiny perturbation of G0 such that that tiny perturbation will lie in this set. Choose G0. Can I find perturbation lying in M of U? So that's the question. So let's do that. So there's my manifold with the metric G0. Now there's my open set. This is the open set U. And what I'm going to do is I am going to do a tiny bump of the metric. So let's take some phi smooth function with compact support containing U. And let's consider a tiny bump, a family of bumps. G of t, which is exponential t phi times G0 when t is between 1 and 0. So G of 0 does nothing. G of 1 is G of 1 is just a tiny bump there. It's like this, right? This would be for the metric G of 1, and the G of t's, they are just a way to interpolate between the original metric and this bump metric, right? It's just a tiny one-parameter family, okay? So the first remark is that if I do this, then of course the volume at the final time is bigger than the volume for the original metric, because when t is bigger than 1, this, so it's positive, I don't know, positive function, non-negative function. So when t is bigger than 1, that this number is strictly bigger than 1, and so the volume has just increased a tiny bit. And so if the volume increased, I know that eventually some p width for this metric has to be bigger than the p width for that metric, because the asymptotic behavior of this nonlinear spectrum just depends on the volume. So there exists some p bar such that, so by the Wey law, implies that exists some p bar such that the p bar width with respect to the metric G1 is strictly bigger than the p bar width with respect to the metric G0, just because we increase it a bit, right? So now let's suppose by contradiction that no metric in this one parameter family lies inside U. So suppose that no G of t lies inside M of U for all t. So what does this mean? This means that initially my metric has the property that no minimal surface passes through U, because if G0 lies inside M of U, I'm done, right? And so now I do this bump, and if no family, if no metric in the family ever lies in the set M of U, this means that I'm doing the bump, but no minimal surface intersects U, so all the minimal surface are always outside the set U. And in particular, because outside U the metrics are the same, this means that I'm changing the metric, but the minimal surface are not changing. Okay, so that is the key thing. Then, because the metrics outside U are identical, this means that the family of minimal surface is the same. Okay. So now we can start seeing things going in contradictory directions, right? Because I know, so I do this one parameter family of change in the metric. I know that the minimal surface remains the same, but the width are changing. And I know that the width are related to the minimal surface by the Minimax theorem. So I want to use the Minimax theorem to get a contradiction on that. Right? Okay. So let's do this. So by the Minimax theorem, so the Minimax theorem implies that the range of this p bar width for g of t, that this is a real number, but this real number lies in the space of all possible linear combinations with positive integers of areas of minimal surface. So this number lies in the following set. The sum, say when L goes from 1 to some Q of NL, area of some sigma L, where sigma L is a minimal surface with respect to g of t. So this is the one consequence of the Minimax theorem, is that this number you can represent as a linear combination with positive integers of areas of minimal surface, right? Because there's always the issue of multiplicity. But we already saw that this set is not changing, so the minimal surface are the same. So whether I put this or that is the same thing, because the set is the same. So in particular, the range of the function, the range of this, this p width always lies within the same interval. Let's call this R, right? So now the fourth step is to show that, well, without loss of generality, when I choose G naught, I cannot choose G naught to be bumpy, because I know that bumpy is a generic condition. So the closure of all bumpy metrics is everything. So G naught without loss of generality, G naught is bumpy. And if the metric is bumpy, the critical points are discrete. And so if the critical points are discrete, this set is discrete. And in this case, we can apply that R is discrete. Okay. So now we are done, because the function t, the function which sends t to the p bar width with respect to g of t, this lies in a discrete set and is continuous. And so if you have a continuous function whose image lies in a discrete set, the continuous function has to be constant, right? And so this implies that the function is constant. It has to be equal to the first width to the one at g naught for all t, which contradicts this guy, right? Which contradicts star. And so, and this contradicts star. Dicts star, okay. Okay. Is this okay here? Sorry. Yeah. The idea is simple, is that to prove denseness, you take your metric, you do a tiny bump that increases the volume, and then you assume by contradiction that no critical point intersects that set. And so if no critical point intersects that set, it means that the critical points are not changing, even if the metric is changing. But on the other hand, you know that the spectrum has to eventually increase because of the Vi law. And then use the fact that the spectrum can always be realized just by a linear combination of the areas of the critical points to get a contradiction. Okay. the proof of Cairi to get the existence of the closure geodesics follows the same pattern, but there he uses a different spectrum and a different Weyl law and different Minimax theorem. Okay. Okay, so now let's do so let me tell you the key idea for the equidistribution result. Okay. So the bottom line will be the following. In the denseness result follows from exploiting the Weyl law against the continuity of the width. The second result will exploit the Weyl law against the differentiability properties of the width. I'll do the same thing but take derivatives. Okay. So let's do this. So in this case, let's choose phi 1, phi n, a countable basis. This is a countable number of functions which are dense in continuous norm, which are dense in C0M. Okay, so I don't know. A countable basis of smooth functions which are dense in the sup norm. So let's choose this. Now I'm going to do something that's going to look a bit weird, but then as soon as I write down this complicated expression and as soon as I write it down, I'll say why I wrote it down, and then it will become obvious that was the reasonable thing to do. So let's do this first step, which is the following. So let's consider a conformal deformation of the metric. Given T now is a vector in the cube of length 1. So this is an n-dimensional cube. Given T a vector there, consider the following conformal deformation. G of T, which is E, and then I sum 1 to n of Ti, the ith component of the vector T, times phi of I, where this guy's there, times the original metric. Okay? So this is a conformal deformation of the metric G. And now let's write the following function. Okay. So let's write the following function. So consider phi of p. This is a function from this n-dimensional cube into the real numbers, and the expression is going to be the following. Phi p of t. This will be the natural log of the p width with respect to the metric G of t. And now I'm going to subtract minus n over n plus 1 times the natural log times the volume of m with respect to G of t minus the natural log of p over n plus 1 and still minus the natural log of alpha n, where alpha n is the constant in the Weyl law. Now, why would I consider that function? Because the Weyl law says that this function is going to a constant, that this function is converging to 0 uniformly. So what I did was I wrote the Weyl law, I took the natural log on both sides, and I subtract one from the other. So the Weyl law says that the Weyl law plus some lemma. So the Weyl law says that the function goes to 0 pointwise. We can actually see that goes to 0 uniformly. Plus a lemma implies that in L infinity, this goes to 0 on the cube as p goes to infinity. So this function is converging to 0 uniformly. Okay? So it's good practice to each time you have a function who's going to a constant, you should take the derivative. Right? And so this is what we're going to do now. So at this stage, let's not worry about whether we can differentiate things or not. Let's just take the derivative and see what we get, and then we worry about that later. Let's see, yeah. So assuming one can differentiate okay, then we can compute that because I know explicitly what the metric is, I know what the derivative with respect to the metric is, I should be able to compute that derivative. Assuming we can differentiate, then we know that the partial derivative with respect to ti of g of t, this is just phi of I times g of t. And so using this, with a bit of work, one can show that the partial derivative of phi p of t, this is equal to n over 2 times the integral of sigma p of t times phi of I minus the average of phi of I on the whole manifold, where this guy is the minimal surface that realizes the p width, where sigma pt is minimal surface. Let me just write, is the minimal surface. Such that the area of this minimal surface is the p width. So using the Minimax theorem, assuming that this minimal surface changes continuously as the metric changes, and assuming that we can differentiate that, then this is a derivative we got. So now we are in a good spot, right? Because we have a function which is converging to 0. The derivative should go to 0, right? But the derivative going to 0 is just saying that these guys are being equidistributed, right? And so let's keep doing wishful thinking. And so if not only we can differentiate the phi p's, but if they are uniformly C1, if phi p are uniformly C1, then we get that the gradient of 5p at t has to go to 0 as p goes to infinity, because if you have a function which is going to 0, and if it's uniformly C1, then the derivative has to go to 0 at every point, right? And this implies from this expression that the integral of phi I of sigma p of t, if I average, this converges as p goes to infinity of the whole average on the ambient manifold, and this for all I going from 1 to n, right? So what this says is that assuming all these awesome conditions, then this minimal hypersurface that realizing the width, they are equidistributed with respect to the first n functions in these bases I chose. But of course, because now the result does not depend on n, I get that they are equidistributed for every possible element in the bases, and so they are equidistributed for every function, right? And so hence, this would give a stronger version of the result. Okay. So now, of course, what happens is that in reality, this function is only Lipschitz, and Lipschitz functions, they are only differentiable everywhere, and so it's possible to have a Lipschitz function which converges to 0, but such that the derivative never goes to 0. So let me just say this. In reality, phi p is only Lipschitz. And so the problematic example, it's like a seesaw, right? Example is something like this. This would be the interval, I of n, and the function be just, suppose that it's just a real line, and the function just being like a seesaw, like the gradient always 1 and minus 1 oscillating a lot, right? Okay. In this case, this function is Lipschitz, if the slope is always 1 or minus 1, is uniformly Lipschitz. Its oscillation is going to 0 uniformly, but still there's no point where the derivative goes to 1 or minus 1, right? So it's because of this example that we get equidistribution, not in the stronger version, but in terms of this sum of the first q terms. So I'll just write here what's making the connection, and then I'll stop. So the correct way of doing this, I don't know, I forgot. The right way. The right way is the following. So there's a weak derivative for Lipschitz functions. It's called, in applied math, people use it's called the Dini derivative or something like that. And it's like the Clark derivative. And I put it like this because it's like a weak gradient. It's this. So this is the convex hull of all vectors V such that there exists a sequence Ti converging to T, and the gradient of the function at Ti converges to V. So the function is Lipschitz, so it's differentiable almost everywhere, which means that at the points at which it's not differentiable, I'm looking at all possible limits of the derivatives, and then I take the convex hull. For instance, if I do this on this example, here is 1, here is minus 1, but at this point, this convex hull will be the interval between 1 and minus 1, right? So now the statement is that if you have a function whose Lipschitz and whose oscillation going to 0, it's not that there's a point where the derivative is 0. The statement is that there's a point where this weak derivative is 0, and because it's a convex linear combination, that's why we have to take the sum. So let me just say the lemma is that phi p of t going to 0 as t goes to infinity, then, or this guy going to 0 now infinity implies that there exists some t bar such that the distance between 0 and this weak derivative at t bar goes to 0. Okay? And then, so I don't have a point where I can't say that the derivatives go to 0 like this. What I say is that there's a certain convex linear combination of limits of derivatives where that goes to 0. And then if we go through the same ideas and then use some combinatorial lemmas, we get at the desired result, which is writing in this form of sums. We get at the desired result after some work. After some work. Okay, so I'll just stop here. Yeah.
Any questions?
So, what about the error term in this file law?
It's I would love to know that. The hard part is that
Yeah, I mean, there are no examples.
there's how can you
But
how
I
can
mean,
you
so.
the
I mean, I don't know.
yeah it's hard to say.
There's close connections with geodesic flow.
But there, in that case, you have the Selberg trace formula, and that gives you, allows you to estimate things in a precise way. In this case, there's no, it's not that there isn't. It's more like I don't know what it is, but I would love to know what is the constant and the error term, and to have an idea what should it be there. Gromov, he kind of alludes in a paper that should be related with the curvature of the ambient manifold, but I have it doesn't mean anything. Yeah.
Well, in the interest of time, let's stop there.